Today we're going to be looking at a new meter. This is sold under the Tekpower brand, and it's a part number YX360TRE-B. This meter came with some very cheap quality probes. Really, it doesn't matter for this meter. It can't read very high currents anyway. And you can see it comes with a little fold-out manual. If you look at the meter, there are no cat ratings. They just give you 1,000 volts, RMS, AC, or DC. You wouldn't expect a meter like this to be certified or anything. It does, however, have a CE mark in the upper right-hand corner. I'm not sure why you would buy an analog meter today. You know, the digital meters have been out for many, many years. This is a picture of me on, I think, maybe my 13th birthday, and I'm holding my first Radio Shack meter. Prior to receiving this, I had been using an old vacuum tube voltmeter that somebody had given to me. I actually used this meter for many, many years. Damaged it quite a few times, but once I got my first digital meter, yeah, I never went back to analog. This is really the first analog multimeter that I've owned since I had that first meter. Unless you want to count this one, of course this was made by Central Scientific. Face on this is actually glass. You can see here it's got two voltage ranges, a 5 volt and a 0.1 volt, and then your galvanometer. I think the last time I used this meter I was showing how to measure current with it. Up in here I had a couple of protection diodes and some resistors, I think, for my shunt, and that is basically to prevent the meter from swinging one direction or the other too far and damaging the meter works. Of course, you can see this meter can read both positive and negative, where this meter can only read one direction. Very similar to my first meter. You can just see how bodged up this circuit board is, and that's because this is a one-layer circuit board. See a couple of diodes in here, mostly resistors, and a large selector switch. I got a little trim pot here to adjust the ohms ranges. I'm assuming this is some kind of calibration pot. And a glass fuse. Now again, this is a 1/2 amp fuse. You'll notice there is no high current fuse, but this meter is not capable of reading anything over, see, 250 milliamps. That's the end of it. But we can see it does have a 50 microamp range. So if you'd like to have a look at the circuit board itself, so yep, just a large selector switch. Bottom of the basement type design. You can see a little ball D10 in here. That's all there is to this meter. Just basically a large divider network. One thing about this particular one that my meter did not have, we can see here it's got a little beeper. This can actually beep in continuity mode. And you can see even the stamping for this is the same on both sides. So when you install the batteries, better make sure that you read the polarity on them. See, it comes with a little spare fuse here. I think, yeah, right, so it's got a little LED up in the corner here, and that's for the continuity test. This center screw, this zeroes out the meter works. So if we're looking at this face on, what we would want to do is make this adjustment. You can see I can either turn it up or down. So we would use this to zero out the works. So I have to look at it face on. And then once that's zeroed, that's it. We don't ever adjust that again. Anything else that's going to be off in the meter, we would trim that with the resistors below. You can see it's got this little chrome face here. So this is so we can see the reflection of the needle, and that just helps us kind of make sure that we're looking face on to that needle. So on the right we have this other dial, and this is used to zero out the meter. Typically a meter like this isn't going to need any batteries in it to measure volts, but it does for measuring resistance, obviously. So the way that this knob works is we short our leads together in the range that we're looking for, and we would adjust this to read 0 on the right hand side. So this is on the 10x scale. You can see I've got a 1K ohm resistor selected, and we're reading 100. So 100 times 10, 1000 ohms. So this would be 10K. You can see it just barely registers on the meter. So you would throw this to the 100x scale. It must be fairly close on the one side. Yeah, pretty good. So let's try 100K. And again, we'd have to adjust this up. We can see we got 100 here. And let's go to a meg. And we can see there's our 100. And let's try it at 10 meg. Oh, that is the end of the upper limit. There you go. So there's 1000, and again, let's put a 1 meg in. It should read 100. And we'll put 100K in. That should read 10. You can see this side of the scale. It's off quite a bit. So the meter itself isn't very linear. You know, but again, this thing only costs $15. I'm not expecting it's going to work very well. So let's see, in continuity mode, you can see it's got a little LED up in the corner again that tells you when it's making continuity. The only thing, of course, you can see the meter will swing, and it's got the beeper. Let's try it with a 50 ohm resistor in the continuity mode, and we can see it reads just about 50. Let's try her with a 1 ohm, and we can see it's reading just about 1 ohm. So one of the problems with these meters, like I say, is that you can overdrive the works and actually jam the meter to one side or the other and bend the needle. I've done that actually on some of the old meters. I've actually taken the needle right off of the works. That can actually happen. You have to be kind of careful with them. So let's just try this with a 9-volt battery. And we can see it's reading roughly 9 volts. Now, let's say I were to have this in the 0.5 volt, so I'm expecting this meter would just go bang. But this meter has probably got protection against that. So it slams, but not hard enough to actually bend the needle. So they've actually planned for somebody screwing up and doing something like this. So let's try driving it backwards. Same kind of thing. You can see it returns to 0 very nicely. No real issue. That's one of the nicer things with a digital meter, especially with auto range. All this would be taken care of for you. So obviously this battery is DC voltage. So if I hook this thing up in the AC volt mode, like any other voltmeter, you would expect this thing, if it's in AC volts range, to read 0. Because there is no AC voltage. You can see if I set this to the 50 volt scale, this thing is showing me reading roughly 19 volts with this meter. Now if I reverse the polarity of this, let's see what happens. Now you can see it doesn't read anything. See that? Flip the polarity back around, and it reads. And I'm assuming that's the same way in all ranges. Now I can tell you that a good analog meter is not going to do this. So we can see the meter doesn't have capacitance testing. There's no diode check really per se. For diode checking, what we can do is place this in the lowest resistance range. And we'll go ahead and attach our diode here. And we'll see the other way it won't conduct. Just looking at the input resistance of this, changes quite a bit depending on what range you're running at. So in the 10 volt range it looks like about 2 meg. 1000 volt range it's a little over 11 meg. With a 1000 volt DC range it looks like about 20 meg. All the way down to the DC half volt range, which is about a 10K ohm input. This is definitely not a high impedance meter. So currently I'm putting out a 2.5 volt sine wave. So the meter will actually swing full scale one direction. And we can see with the Bryman, With our bar graph here, it's reading up to the 2.5 mark, and same thing with our unity meter. So the nice thing with the digital meter, obviously we can see this one's reading a negative 2.5 as it's working its way up the bar graph. And with the unity, we actually have a bi-directional bar graph. So this is more like the antique analog meter I showed, where it can swing both positive and negative. Obviously, again, this meter can only swing one direction. So currently what I'm doing is outputting a 5-volt signal with a 2.5 volt offset. So if we're looking at our second scale down, we can see it's a 10 volts full scale here, down to 0. So the center point is our 5 volt. And let's just compare how fast the response is of these two meters bar graphs versus our analog meter. What I'm going to do is change this over to a triangle wave so we'll get a nice linear sweep up and down. We'll take it up to 500 millihertz. And we can already see our meter here is having some problems with this. So it's not quite reaching the full scale. Of course, with the digital meters, you have functions like min, max. This has got the crest factor. So this is with a square wave. You can see our analog meter now is overshooting about maybe a 0.5 volt. So unless they were to dampen this or filter this input signal down a lot, we're basically at the mercy of the mechanics. I'll go ahead and take this frequency up a little higher. Again, we'll just keep it on a square wave. Now this is with 2 hertz applied, and again, no problems on these bar graphs, but we can see our analog meter, again, it's really dampened that signal. So this is with 4 hertz applied, and we can see now the analog meter is really beginning to attenuate this signal. But again, our two digital meters are still showing this full scale. Now, a lot of the digital meters can't do this. These two particular meters have the fastest update rate for the bar graphs of the ones that I've looked at. So this is looking with 10 hertz, and now we can see there's just hardly any deflection with our analog meter. And you can see this thing is going to start slowly drifting up and down, and that's as this frequency is beating on the sample rate. We get that aliasing effect. But our Bryman over here, you can see, is still making full use of that display. Now, that's the one thing about this Bryman. Of all the meters I've tested, this has had the highest usable bandwidth for that analog bar graph. So right now I'm applying a 60 hertz sine wave, and this is roughly 5 volts, and we can see it's 60 hertz on these two meters. Of course, with our analog meter, we don't have a way to measure the actual frequency, but we can see it's in our center point of roughly 5 volts. Now what I'm going to do is offset this a little bit. So we can see as I add a negative offset versus a positive offset, this has a dramatic effect on our analog meter. Of course, it doesn't have any effect on our two digital meters. But let's just have a look at the bandwidth of this meter. So you can see I'm outputting 100 kilohertz right now, 99.98 and 100 on the Bryman. And you can see all three meters are still reading roughly the same value that they were at 60 hertz. This is with 800 kilohertz applied, and we could see we're reading roughly 3.5556 with the Bryman, and again roughly 800 kilohertz, and it looks like about 3.17 with the unity. And again, we'd have to select our frequency input to be able to read this, but you can see roughly 800 kilohertz there. But on our analog meter, you can see it's about 2 ticks beyond, so about 4.4 volts off of this. So this is now at 2 megahertz. One of the problems with the meter is this is what we're injecting the signal with. Not really what you want to be using for this kind of frequency. Unfortunately, there's not a good way to tie into this meter, but you can see we are still reading roughly 3.6 volts or so. So not much of a roll-off compared to these two meters, which, you know, this is basically reading 0 now, and 0.7 volts on our unity. This is one area where an analog meter like this may actually be useful. As you can see, I've got the high voltage power supply out, and currently all three meters are attached in parallel, and we're outputting somewhere around 24.5 volts, and we can see it's just shy of the center mark, and this is on the 50 volt scale. I'll try to get as much in the picture as I can. So let's go ahead and we'll take this on up. So roughly 50 volts. We'll go to the 250 volt scale, and we can see all meters reading roughly 250 volts. So let's go to the 1000 volt scale. So we're roughly in the center point, and we're about 500 volts now. And again, this is the top end of our power supply. So roughly just shy of 1000 volts, 981 versus just a tick under 1000 volts. So currently this is a 50 hertz square wave. You can see it's 545 AC plus DC, or 545 AC and roughly a half a volt for the DC content. And we can see roughly on the Bryman over here, again, it's about 600 millivolts high for the DC content. So basically I have the power supply set for 0 volts offset. And again, we can see the AC content of this is 543 versus 545. Now when we look at our AC volts on this meter, again this is on the 1000 volt scale, we can see it's reading roughly 635 volts. We are feeding in a square wave, but you can see it's not causing any problems with the meter to run the AC frequency in. Again, fairly high voltage, and again that's the maximum I can put out with this power supply. One of the things you notice on the Unit T is the bar graph is just slightly under the halfway point. When I first bought this meter, I charged it, and then after all of our testing and modifications, I had about 40 hours or so operation on it, and I went ahead and recharged the battery, and it hasn't been recharged since. So I probably have somewhere around 25-ish hours now on this meter since I bought it. So it doesn't get used all that often. It's been used mostly for benchmark comparisons like this. But eventually here we'll have to recharge this thing again. So I'm looking at transient testing this, and one of the first problems we run into is of course our connectors won't fully engage. So that's not going to work. You can see I have another style of this type of connector, and again of course these don't engage either. I could run it with an open banana like this. Of course these are going to plug in just fine. I don't like having that metal exposed though with this transient generator, especially when we run the big one. So I bought these type of connectors for my HP 3468 multimeter, and you can see the sheave just retracts down into the case, and I think that's what I'm going to use. Of course these fully engage. Before I run this meter, there's one last thing I'd like to show you. I've used in some of my leads here that I've made up for the transient generator to plug a good set of test leads into it. You may remember I was trying to ohm out 5kW's meter, and one of the things I'd mentioned is that I would like to have a programmable threshold meter, because what will happen is the Bryman will just beep, and then you have to wait for the resistance to kind of stabilize. But on this meter, you can see as I kind of slide the pins across, it's like, oh, that's definitely not a short. Oh, that's a little higher. Oh, so I can go across with this meter quite a bit faster and find that pin. So what I'm going to do, I'll put this thing in the lowest range, and I'm just going to sweep across this thing pretty quick. You can see there's a little bit of conductivity right in there, but I can go across this pretty fast, and boy, as soon as it hits it, we're right there. Of course that could be putting several milliamps through our device in this mode. Let's just have a look. Yeah, see that? 130 milliamps in the conductivity mode. So way higher than any meter I've ever looked at. It's probably one of the reasons that you wouldn't want to use this for sensitive electronics. Let's just try it in the 10x mode and see what we get. So about 14 milliamps in that mode, which is still pretty high. Let's try it with 100x. There we can see about 1.4 milliamps. That's still pretty high. A lot of the meters will read sub 1 milliamp. Okay, the first test we're going to run is our static discharge test. There are no real sensitive electronics in here. Hard to believe that this would cause any problem with a meter like this. They're just made so cheap with all passive components. You think this would just go through just fine. Okay, that's it. We'll go ahead and functional test it. Okay, the meter did just fine with that. What we're going to do now is apply our AC line voltage. Again, this is 220 volts and it's full wave rectified. And then we're just going to select each function of the meter. So 10 volts. It's interesting, I can see how much current it's drawing on our meter over here. This is reading out in milliamps, the current draw. So it's drawing roughly 52-47 milliamps. Oh, it just fried it. Why? Yeah, I heard one of the resistors just give up. Yep, definitely fried. It looks like R22. Whew. Burned the coating right off of her. That's something I would have done as a kid though. Boy, I remember having to change the resistors out in that Radio Shack meter more than once. So we'll go ahead and zero this out. And let's have a look here. So this is a 10 meg. That's about right. And a 1 meg. That looks good. And a 100K. Let's just go ahead and we'll set this real close to the 10 mark here. And we'll switch it down a scale. And let's go to a 10K. And we'll switch it down the scale. Let's go to a 1K. Oh. Yep. So it's definitely damaged it. This should be reading up at the 10 mark. Well, I guess I'm not too surprised by that. So let's continue on with our testing. Oops. Hear it right there. Let's turn off our line voltage and let's just run this thing in our standard transient mode. So this is set for 1000 volts AC, and I'm going to run this thing only in the 1000 volt AC mode. Let's just see what happens. So we'll start off with 1000 volts. So you can kind of see how this works. Is I apply a transient, I turn off the AC line voltage, I apply the transient, and then I reapply the AC line voltage. So that's how this transient generator works. And I do that because I don't want that AC line voltage to sustain an arc. So let's go ahead and we'll take the voltage up a little higher. So this is going to be 2000 volts. Let's try it in the DC volt range. Again, this is 1000 volt DC. You can try it on the 250 volt level. So this is in our 250 volt AC mode, and I've disabled our AC line voltage. But you can see the meter doesn't even flinch with this transient. That's because the pulse width on this is only 100 microsecond wide. So let's go ahead and we'll take the voltage up higher. So this is going to be 4,000 volts. Again, 100 microsecond full width half height. Let's just see if the meter will even budge now. Oh, didn't like that, so the meter's opened up. So it looks like this R22 here is opened up completely now. It also would appear that these diodes up in this area have shorted out. So again, if you look at the meter, it's a very simple design, so it's definitely something that could be repaired after a transient like this. That was one of the nice things with a meter like this as a beginning hobbyist, is I was able to actually keep that meter repaired when I would do things that would damage it. I found this meter actually listed under 5 different brands. Again, when I bought it, it was sold under the Tekpower brand, but it's also listed under Sunwa, Sanwoo, Samwa, Sunwi, and Sanwa. So yeah, I'm not sure who actually makes the meter, but like I said, the schematics were available for it online. So the components here that are in pink are what I damaged. So R26 wasn't open, R21 wasn't open, D2 here was a short, and D3 was shorted. The other thing that I did was blow the fuse open. So there's some discrepancies between my meter and this one. Mine has a beeper, and that beeper is tied in parallel with R20, and then they've changed the value of R20 from 18.5 to 22 ohms. They also have an LED in here, and the way this works is they use R21 either for part of the divider, or they're using it for the current limiter for the LED. So when the switch is in the continuity test, or the 1X, the voltage passes down through the LED, and then they're using this R21 for the current limiting resistor for the LED. When it's in the 10X mode, the LED becomes reverse biased. Now we basically use R21 for the divider. So just to save a little cost there is what they're doing. I also noticed that R19 on the circuit board is actually screened as R16. Right here it shows R16, and that's actually R19. Then if we look right here, we see another R16, and that really is R16. This resistor here is not screened at all on the board. This is R13. Another thing I noticed is this is the common point right here. This is R18 and then D1. On the schematic, they show these two as being swapped. The next thing I noticed is the fuse is not tied off of the plus input. It's actually tied in the common side. So we can see this is our common lead here, and this goes straight to the fuse. So that fuse is actually in there for all the protections. It's not just there for the current mode, it's in there for every mode of the meter. Another thing I saw with the schematic that had me a little confused is this line here passes right around, and then there was no dot. Normally, like here, you're assuming that that's not a connection. Normally what you would do is you would tee this line off so you never have 4 wires coming to a junction point. And this actually is a junction point, so I kind of scribbled this out and redrew the wire here and here. So what I've done is I've replaced all these diodes with a 4007, and the reason I've done that is these diodes are rated for an amp, where the original 4148s are only rated for a half an amp. And what I'm afraid happened is we damaged these diodes before it actually blew the fuse open. another thing I've done is put a Schottky diode in series with the batteries. So there's 3 batteries again. These are the AA's, and then over here is the 9 volt. The way this would work now is if I get a positive transient coming in here, it would normally have damaged these resistors. So now what I've got is a TVS sitting here. This is a 11 volt TVS, and that's tied to this center swipe. So while this thing is in resistance mode, if this voltage at this point gets higher than the ground point by 11 volts, I go ahead and conduct all that current through the fuse and blow the fuse. If we reverse the voltage, so if I put a plus on the common and a minus on the normal input, then voltage feeds through the TVS, and it gets blocked by this Schottky diode. But then if it's high enough voltage, it actually conducts through this TVS and then back to the input, and again draws enough current to blow the fuse open. Another thing that had happened was the LED had blown open. One way that could happen is if the swipe was across the 10x, if we put a positive voltage on the common input relative to our input, and then the voltage would feed back through the resistor, through the diode, and then through the switch, and then through the battery, and then back around. So this would handle all that current until the fuse blows. So now what happens is all the current comes through the common, goes through the TVS directly into this location, and then back around. So this drop is going to be less than the resistor and the LED, so this will absorb all the current in that case. The other direction would be we reverse bias this diode, and in that case we're limiting the voltage across this arrangement to what the voltage drop of this TVS is. One of the things that's interesting about this meter is they've added this 9 volt battery just to be able to measure a higher resistance value. So that's the only time this 9 volt battery is used. So I was actually thinking you could have just ran this off of a 9 volt battery, changed all the values here, jumped this thing out, and just run it off of that. So I'm not really sure what the reason was why they just didn't run it off a single battery. You can see this is what happens when you don't use the hot glue gun. You just melt the glue with a soldering iron. And you can see here I've changed out all these diodes, and I didn't quite have the correct value resistor here, so I strapped a couple in parallel. I had some good resistors for these other 2 that I blew open, and we've gone ahead and changed out the fuse. Another thing I was thinking with the meter is we could maybe substitute this fuse with a poly switch. Now that we have these larger 1 amp diodes in here, it may actually be able to blow a PTC like that open. We just have to try it. Again, it's hardly worth putting a whole lot more time into it. I just wanted to show you that we could get the meter working again. And you can see I can still adjust this. Works fine, and all the ranges. Of course, this is your highest resistance range, so I'm just touching the 2 leads with my fingers here. I don't have my AC voltage source available, but here you can see it in DC, so this will be 5 volts, which will be center scale on the meter. Again, remember this where we put in a DC voltage and it actually shows an AC volts. The reason the DC voltage affects it, it goes into the input through this R13 into this divider network, and then through the switch up through the diode and into the meter. So this blocks the voltage when I flip the polarity of the input. Really what should have happened is we should have had a capacitor in series with this resistor, and then that would have removed all the DC. They have this output pin here. You can see it's actually marked on the meter as an output. And if we look in the manual, see, it shows number 5. And number 5, it just says output series condenser terminal. See, and then it shows here AC test on output terminal. Plug the red test lead into the output socket and the black one into the common. Set the range selector to the selected range position. Connect the test leads to the circuit to be tested and read the scale in the same manner as ACV test. Such a measurement is made to block the DC voltage which presents in the same circuit. It must be cut out so that the AC voltage can be read alone. So this is actually what they're trying to do. This isn't really an output. This is the input. And it's just tied with that blocking cap. Really what they should have done is they should have tied this node right here back to that node there. The only problem with that is that this capacitor is so small it won't give us the AC response we need to read 60 Hertz. It starts working at about maybe 400 Hertz. You'll start to see a very flat response come out of it. So the value of this capacitor would have to change in order to make that work. So I think that's going to be it for this review. Again, I'd like to welcome all you new members. Till the next meter.